Hello, welcome to today's class. So we'll continue our discussion on Prolog fact and rules. So we had been using this family tree as an example, and we have already seen how to represent the parent relation as a fact using a binary relation, and how to represent the gender again using fact using a unary relation. And then in the last class we also see how to represent the mother relation using rules, and there where we stopped our discussion. We executed some programs and saw the outputs, but now to understand the rule, there is something called a definition graph, which helps to understand what the rule does, and actually it may also help you to come up with the rule by first constructing the definition graph. So for the mother relation, this is how the definition graph looks like. So let me first tell you what a definition graph is. So in a definition graph, you have nodes and you have arcs, and the nodes, they correspond to objects. Uh, for example, we have objects like Pam, Bob, and so these are the different objects that we have, and these nodes can represent objects, or we may use variables which will be placeholder for the objects. And then the arc, they represent binary relation. So for example, if I have a arc from x to y, so it's representing the binary relation parent, and it says the x is the parent of y. So from where the arc is originating, that will be your first argument, and where the arc end, that will be your second argument. So this is how binary relation will be represented. And unary relation, for example, the gender, so x is female. So here when I say when I put female here, it means this node, whatever object I put here, has to be female. And a new relation is defined by the dashed arc. So what this diagram says is that if x is the parent of y, and if x is parent, then x will be the mother of y. So the relation represented by the solid arc hold, then the relation showed by the dashed line will also hold. Sometimes it is easy if you come up with this type of a graph first and then try to write the rule, or and other times if you already have the rule and you want to understand, you can draw something like this, a graph. Now for the grandparent relation, this would be the definition graph. So it says that if x is a parent of y and if y is a parent of z, then x is the grandparent of z. So clearly this graphs helps you to understand the grandparent relation because it shows the hierarchy. So when I say y is the parent of z, so z is the child and y is this parent, and the parent of y, who is x, so x has to be the grandparent of z. So once you have the definition graph, you can create the Prolog rule for it. So we say that x is a grandparent of z if x is a parent of y, that's why we write this goal, and y is a parent of z, so that's why we have the second goal. So once you write, if you draw the definition graph, you can then create the Prolog rule. This is another way to represent the same rule. So we are writing the head, the conclusion part in one line, and we are representing the individual goals in separate lines. So we have two goals in the body and we are writing them in separate lines. So this is another convention you can use to write the rules. Now let's talk about the sister relation. So this would be the definition graph for the sister relation. So both of them, if X has to be the sister of Y, both of them have to have a common parent, and X has to be female, then X will be the sister of Y. So they need to have a common parent, Z. So Z is the parent of X and Z is also the parent of Y, and X is female. In that case, X will be the sister of Y. Another way of reading this is, for all X and all Y, X is a sister of Y if both X and Y have the same parent and X is female. And now we are ready to write the rule for the sister relation. So whatever is represented in this graph, we are just writing it. So X is a sister of Y if we have a Z is a parent of X, then Z is a parent of Y, and X is female. So once you have this graph, it's easy to write the rule. But this rule has a problem. If you try to execute it in SWI Prolog, for queries like this, it will be fine. If you go back to our family tree, you will see that N is actually a sister of Pat, and hence it will return true as the correct answer. But if we put questions like who is the sister of Pat, then we'll see that the way we have written the rule is not perfect. When we execute this query, it would first return N, and if we press semicolon, it will represent Pat. So what it is saying is that Pat is a sister of Pat, which is not logical. However, if we write our rule in this way, it will also say that Pat is a sister of Pat, and that's happening because our query is X comma Pat. So X remains as X, but Y is replaced by Pat. So we are trying to find out whether X is a sister of Pat or not. And now Prolog, when we are asked this question, will try to replace this variable with all the objects. So it will try all the objects that has been defined, and since Pat is also a object, so it will replace X by Pat also. And what will happen when you replace X by Pat? So then we'll see that this node is also Pat and this node is also Pat. So definitely Pat will have a common parent. The same parent will be the parent of Pat and this Pat also. And Pat is already a female, so we'll say that Pat is sister of Pat. So that's a problem. So how do we fix this problem? And this is how we will try to fix the problem. So not only we should have a common parent and X should be female, and it should be the case that X is not equal to Y. So meaning of this line here is X is not equal to Y. So Pat cannot be the sister of Pat. So we want to discard that possibility, and for that reason we have put that X should not be equal to Y. It should not be the same object. In SWI Prolog, this is how it is in book. Actually, this is how it's not in the book. The book uses another convention, and if you follow the convention in SWI Prolog, it will not work. So this would be the correct format to represent not equal. And now if you run this query, as before, it will say that N is the sister of Pat. So for this query, true will be returned, and for the second query, it will return only N. It will not return Pat. So now this definition of this rule is perfect now. So with that, I'd like to end today's class, but before that, I'd like to conclude few things. So Prolog programs can be extended by writing new clause. So you can write in the Prolog program, you write clause. So what are the different types of clause? There are three types of clause. One is fact, which we have already seen. Rules we have already seen, and questions we have already seen. So these are questions we are asking who is the sister of Pat. So we have three different types of clause: fact, rules, and questions. Fact declare things that are always unconditionally true. So when we have a fact, what is specified in the fact will be always true. However, rules declare things that are true depending on some given condition. So conclusion will be true based on some condition. And by means of questions, the user can ask the program what things are true. And a Prolog clause consists of a head and a body. So in case of rules, let me go to a simple rule. So here, this is the head of the clause, grandparent x, z, and this is the body of the clause. So we have a head and we have a body. So every clause will have a head and a body. The body is the list of goals separated by commas. Commas between goals are understood as conjunctions. Conjunction means and operation. It's not or, it's and. Both the goals have to be specified for the conclusion to be true. It's not that one goal is sufficient. So it's conjunction and operation. Now a fact is a clause that just have the head and no body. Because for fact they are unconditionally true, so we don't need a condition part. So your body is missing. In fact, we only have the head, and questions only have the body, and rules consist of the head and the body. In the course of computation, a variable, if we use a variable, the variable can be substituted by another object. We have already discussed in today's class how a variable x can be substituted by objects like pen, at, Pam, and Bob. So a variable x can be substituted by objects like that, and when we substitute a variable by object, we say the variable has become instantiated. And now variables are assumed to be universally quantified. So in the theory class, when we talk about first order predicate calculus, we will see that there are two types of quantifiers. One is universal and one is existential. So here in Prolog, the variables are assumed to be universally quantified, which actually means for all. So if we have a rule like this, we can read that the variable x will be universally quantified. So we'll say for all x and all y. If x is a parent of y, then x is a child. X has a child. So here, as you can see, we are saying for all x and y. So this is universal quantification. Of course, there is another reading possible. The same thing I can say for all x, x has a child if there is some y such that x is a parent of y. So both these readings are possible. So as you can see here, I am not using universal quantification for the variable y. We are not saying all y, we are saying some y. So alternate readings are, however, possible for variables that appear only in the body. As you can see, the variable y appears only in the body, it doesn't appear in the head. So for such variables, it's not mandatory that we have to use universal quantification for all. We need not use for all. We may use alternate readings. So with that, I would like to end today's class.